Welcome to Algorush. We're constantly relying on systems to store our data, trusting them kind of like a black box. But what happens if that trust gets broken? So let's think about two really unsettling questions. First, what if the data on your disk just silently changes, gets corrupted, and you have no idea? And second, how can you possibly update your software without making all your old data completely unreadable? To answer those questions, we need to stop looking at data storage as this mysterious black box. It's time to dive inside and see what's really going on. It all starts with something pretty simple, a file on a disk. It's basically the container for all of our information. But see, trying to manage one single gigantic file is super inefficient. So to make things manageable, files get broken down into smaller, fixed size chunks. And these are called pages. Now, this is where things get really interesting. Inside each and every one of those pages, there's a small but absolutely critical section that holds the key to its reliability, the page header. Think of a data page like a big shipping container. The header, well, that's its shipping label. It tells you everything you need to know about what's inside, how it's packed, and where it's supposed to be. It's the control panel for that whole block of data. Okay, so keeping that in mind, let's tackle our first problem. How does this little page header actually guard against the silent threat of data corruption? And this is a huge deal. Hardware can fail. Bits on a disk can literally just flip from a 1 to a 0 out of nowhere. We have to have a way to catch these little errors before they turn into a total disaster. And the solution is a really clever concept called a checksum. Honestly, the best way to think of it is like a unique digital fingerprint for your data, or maybe even better, a tamper-evident seal. The process itself is brilliantly simple. When data gets written to a page, the system calculates a unique checksum from that specific data. Then, it stores that checksum right in the page header. So later on, when the page is read back, the system just recalculates the checksum and compares it to the value it stored earlier. And here's the crucial part. If those two values don't match, bam, the system knows instantly that the data is corrupt, that the seal has been broken. It's an immediate red flag that prevents a potential catastrophe. So we've secured our data's integrity. Awesome. But what about that second problem? How do we evolve our software over time? Software is always changing, right? New features get added, things get improved, and sometimes that means the format of the data it writes also changes. This can create a total compatibility nightmare. So what's the fix? How can our shiny new software understand data that was written by its much, much older self? Well, the answer, once again, is hiding in that page header. This time, it's something called a magic number. This special sequence of bytes, this magic number, it acts as a clear identifier. It's like a label that tells the system exactly what kind of format version it's looking at. So the software reads this magic number first, before it tries to read anything else. And this little number acts like a universal translator. It tells the new software exactly which dialect the old data is speaking, so it knows how to interpret it correctly. Okay, let's just zoom out for a second and see how these two small mechanisms, these invisible guardians, have a massive impact on the systems we use every single day. So checksums, they give us data integrity. Magic numbers, they give us backward compatibility. And both of them live in the page header, the little control center for our data. All of this together is what creates true digital resilience. And this stuff, it's not just some obscure technical detail. This is the absolute foundation of trustworthy, evolving software. These invisible guardians are working tirelessly inside every reliable system, giving us the resilience we kind of just take for granted. It really makes you wonder, doesn't it? What other elegant solutions like these are out there